All right, welcome to worksheet number 11. It's related rates. This corresponds to section book section 2.8. We'll be given a situation. So here, this section is basically all problem solving, application problems. We're given a situation and problem where different variables are related in certain ways. So we'll use all sorts of differentiation techniques we learned so far, chain rule, implicit differentiation, and all that stuff. Once we know each variable related to each other, we can find the rate of change. Sometimes instantaneous rate change, which is basically the derivative, right? So we use that. Let's look at the preliminary material. Example 1, assume both x and y are a function of t, right? So we have now multiple variables, but t is the variable. It says function of t. That means use t as a variable. So I gave 3 examples. They kind of look the same, but there's like a technical differences. So let's look at the first one. d dt, t to the 5th power. I'm just taking the derivative of 5th power, which is no problem. Notice that t here and then t here matches. So what I'm taking the derivative of and the dt, they match. So this is easier question. So it says 5t to the 4th. Nothing fancy. Let's look at the next one. d dt, x to the 5th power. So I'm taking derivative of x to the 5th, but with respect to t, that means t is variable now. So that means I get 5x to the 4th power, but because I'm not doing d dx, instead I'm doing d dt, I have to use a chain rule, so I have to do dx dt. So I have this extra stuff because the variables don't match. Same here, d dt, y to the 5th power. 5y to the 4th power, and then dy dt. So that's kind of like a review of what we learned in the previous sections. Now we're gonna use in this section we have like sphere, this geometry question, Pythagorean theorem question. We have also like sine, cosine, tangent questions. So these are stuff that you're supposed to know, but we haven't seen. I'm sure for some of you guys, you haven't seen like a sphere, volume of a sphere. You probably haven't seen it forever. So I want to kind of review that. It's 4 over 3 pi r cubed. So if you have a sphere is basically the ball. A circle is 2-dimensional space. Sphere is a ball. So radius is r. So volume is like what's filling inside the ball. It's 4 over 3 pi r cubed, right? So that's that. It says if air is being pumped into spherical balloon, so they have a balloon, the sphere, what happens to the volume as the radius is increased by 1 centimeters? So this is a very typical situation. So let's just make something up. It says give an example to illustrate your answer. Okay, what is that? So basically we'll create our own example. So let's say you have a radius 10. I just made it up, right? Why 10? Just because, why not? So volume when radius is equal to 10, so I can get 4 over 3 pi 10 cubed, right? So I'm using the formula here. I just copy that down. It says volume is increased by 1 centimeter. So I'm going to compare that to when the volume r is equal to 11. Okay. So 4 over 3 pi 11 cubed. If we calculate it out, just put it in the calculator. 4188.8 cubic centimeters. The other one, when the radius is 11, 5575.3 cubic centimeters. So the difference is 1386.5 centimeter. So what that means is cubic centimeters. If the radius is increased by 1 from 10 to 11, the volume is increased by 1386, right? It's okay. So why did I have to choose 10? Like, is it always going to be like that? So just when the balloon is smaller, probably the volume will change by smaller amount. So just to play around, what if when nr is equal to like 2 to 3, right? So if I have a smaller balloon where your radius is 2 and then it became 3, I don't think the volume is going to increase that much, right? Because it's just smaller balloon. If you calculate this out, the volume here is going to be 33.5 volume when radius is 3 is 113.1. So difference is 79.6 cubic centimeters. So this one doesn't have like a fixed answer. So all depends. Do we have like a big balloon? Because if you increase the volume by radius by 1, it increases this much volume. But if you have small volume, it's like only 79, right? So I want to keep that in mind, because later it's going to ask how fast is the volume changing when radius is what. So it depends on what radius, we'll have different answers. All right. Let's look at the second example, Pythagorean theorem. How are three sides of a triangle related? I'm sure you guys remember at some point in your life. I get a squared plus b squared is equal to c squared. So this is Pythagorean theorem. So that's how they relate. A squared plus b squared is equal to c squared. If the hypotenuse, which is the longest side, of the right triangle is increased by 1 centimeter, what will happen to the height? Give an example. Okay, so I'll just create something here. Let's say it's 3, 4, 5 triangle, right? So here, the question is not too clear, but it says the hypotenuse is increased by 1. So what happens to the height? Okay, so I'm going to assume the base is still 4. Hypotenuse becomes 6, right? So the question is what happened? Oh my god, my graph is so out of proportion. So what happens to this guy, right? So how do you find that? Okay, I don't know what this is. So let's call this y, just because it's a vertical distance. So I can say 4 squared plus y squared is equal to 6 squared. So 16 plus y squared is equal to 36. That means y squared is equal to, subtract 16 from both sides, I get 20. Y is equal to plus minus radical 20. But here we're talking about distance, like a length, so it'll be just that. If I calculate radical 20, I get approximately 4.47, right? So 4.47 approximately. So that means it used to be 3, again it went to 4.7, so it's increased by 1.47. So again, kind of same thing. I'm not going to do the other triangle, but if you have different triangle, if it goes by 6 or 7 or whatever, then this might be different, depends on how big the triangle. So they can say, oh, the hypotenuse is increased by 1. What happens to the height? Given that your base is like 4 or your hypotenuse was 6 or hypotenuse was 7, then you'll get a different answer. All right, let's look at the next one, tangent. Okay, so graphically what the tangent represent, let's say this is theta here. Tangent, you can think of it as a sine over cosine, right? So, or however you remember it. So let's name it A, B, C. So tangent theta is going to be B over A. Everyone kind of remembers it a different way. I remember it graphically. I draw it like a T, so it's like that over that. That's my tangent. Some of you guys remember opposite of adjacent. So that's another way to remember it. So, but tangent theta is just that over that. Okay, so I got that. If the angle theta is that is opposite to the height is increased by pi over 6. So this, we're talking about this angle. If this angle is increased by pi over 6, what happens to the height of the triangle? Okay. So let's see how that works. Let's move up here. I'm gonna just create like my own triangle. I'm just gonna make it up here. So I'll have something like this. I made up, so there's 1, this is pi over 6. All right. So this is y. I don't know what the height's gonna be. Tangent pi over 6 is equal to y over 1, which is just a y. I know that tangent pi over 6 is that. If I calculate tangent pi over 6, I get 0.577. So y is 0.577. So the height is 0.577. Okay. So now they are saying, what happens when you increase the angle by pi over 6? Okay, so I'm going to make this angle like higher. So I will, maybe I use red. So maybe something like this. And I want to see how much it goes up by, right? So, okay. So the new angle is going to be the new angle, because I'm increasing the angle by pi over 6. So pi over 6 plus pi over 6. So that's 2 pi over 6, which is pi over 3. So tangent pi over 3, I can calculate it by tangent sine over cosine. So I can do sine pi over 3 over cosine pi over 3, which is radical 3 over 2 over 1 over 2. That's radical 3. If you calculate it out, 1.732. Okay, so from 0.577 to 1.732. 0.577 to 1.732. So that's increase of 1.155. Okay, so that's how much it went up by. Again, depends on what angle or what length you have here, they'll give you a different answer. But these are kind of things we're going to be working with. Example 2, x and y are function of t, then find the derivative. Again, this question doesn't seem like, okay, there's x and there's y, and then they're saying it's t. So t is the variable, x is also variable, y is variable, and then they're related to t. They say to find the derivative. They didn't even say like dx dt, dy dt. So this is not a clear question, actually. Not a clear question. Because they didn't say, do they want dy dx dt or dy dx dt? Because now we have a bunch of other variables, so which one are we talking about? So, but I can kind of get started. I can use, well, it says it's function of t, so t is going to be my variable. But I can still do this much. I can still take the derivative with respect to t on both sides. So this is what I'm going to write like this. And then I go x squared plus y cubed, and then 10 squared, which is basically 100, right? So I can take the derivative with respect to t. I can kind of get started on it. So here, again, I'm adding this plus that, so I can take the derivative of this separately, then add to that derivative of y cubed. So 2x dx dt plus 3y squared dy dt. Again, I am taking derivative with respect to t. This is variable x, that's why I need dy dx dt by using chain rule. Same here, y cubed, that. So I'm doing implicit. And is equal to, I'm taking the derivative. This is just 100, which is constant. Derivative of constant is 0. So that. So I can have this much, right? I can't do much from there. So it depends on, like, do they want dx dt, then I can solve for this. If they want dy dt, I'll solve for this, right? Let's look at the next question. So this is like the real question now. Example 3. Air is being pumped into a spherical balloon. So we talked about balloon, sphere before, at a rate of 20 cubic inch per minute. All right. So I kind of emphasize that here. I'm going to write this. Cubic inches per minute. So this is like a rate. Like when I see something per something, like miles per hour, kilometers per hour, whatever, that's what we were talking about. Velocity, which is a instantaneous rate of change. So this is also talking about instantaneous rate of change, volume per minute, right? So I'm already making a comment. It's like, this is going to be derivative, instantaneous rate of change, which will be indicated by the derivative, right? Of change. Let me just write it, change. So I notice also cubic centimeters, that cubic inch, sorry, represents the volume, minutes represents the time. So my guess is going to be dv dt, right? Volume over time. So I got that. How fast is the radius of balloon increasing when the radius is 6 inches, right? So as I said before, if I kind of scroll up here, I ask same question: how fast is the volume changing? And then, like, well, it depends on what radius, right? So again, like, that's why in this question here too, they're asking how fast the volume, the radius of balloon increasing when the radius is 6. So we'll find the how fast the radius is increasing, then we'll look at a particular radius, right? Okay, same thing here. How fast is the radius of balloon increasing? So that's also an instantaneous rate of change. But this is different than this. So we have two instantaneous rate of change. The answer is yes. One is for volume and one is for the radius. So here I'm going to rewrite it as dr dt. The reason I used r here is they're asking for how fast the radius is changing. That's why I used r. Here, the reason I did v is this is how volume is changing, right? So here we have two derivatives, which is fine. Okay, read this problem carefully. Identify type. This is the volume question. Identify the quantities that change. So dr dt, that's going to change. Here, I'm looking at this. Air is kind of flowing in a constant rate, right? It's going to be always 20 cubic inches per minute. So that doesn't change. So I'm going to kind of separate here. dv dt is like airflow. It seems like it's always 20. Min is fixed. But obviously when you pump in the air, the radius is going to increase. The radius is going to change. The volume is going to change. Obviously the time changes, right? So just by reading this, the rate of how fast the radius is increasing is going to be different. Radius is going to be different. Volume is going to be different. Time is going to be different. Identify the rates that are known and then what is to be found. Okay, so we need to, so this is kind of repeat. We want to find, I forgot what they want to find. I'm reading the question. How fast is the radius increasing when the radius is 6? Okay. To find dr dt when r is equal to 6. What do we know? dv dt is always 20, fixed. We also know that v is 4 over 3 pi r cubed, right? Find the equation that relates to the variable. Oh, I guess I already answered that. So that's what I was going to say, but this is how radius and the volume are related in this way. That's why it's called related rates. Radius is this is volume, this is how they're related. Differentiate the equation with respect to time. Okay. So again, we have v, we have r, we have time. Eventually I want dr dt, so I'm going to take the derivative with respect to t. T is my time, right? So what I'll do is I go d dt v 4/3 pi r cubed. Okay. So on the left hand side is just dv dt. On the right hand side, this is constant, this is constant. So 4 pi over 3. I'm taking derivative of r cubed, so that's 3r squared times dr dt. Okay. Again, the reason I needed dr dt is because I'm taking derivative of r cubed. With respect to t, they don't match, so I need that. Same here. All right, so let's see if I can simplify it. There's 3, there's 3. So 4 pi r squared times dr dt. All right, let's see. So far, that's what I have. I want to solve for dr dt. So I want to move this guy on the other side. So maybe take one more step. Dr dt is dv dt times 1 over 4 pi r squared. So I started with dv dt from here is equal to all this. That's that. But eventually I want to solve for dr dt, right? That's what we want to find dr dt. That was the thing. So like when I'm here, like how do I solve for that? Dr dt. I'll just have to divide by this. So dv dt times 1 over that. So I have that much. Okay. So next step is, do I know dv dt? Let's go back here. What did I say? Oh yeah, dv dt is 20. Okay, got it. So dr dt is equal to 20 times 1 over 4 times pi times r squared. So again, like, depends on what radius we have, we'll have different rate of change. I think the question specifically asks for find 6, right? Because he says specifically, it says radius is 6 inches. So let me go down here. So I can do 20 over 4 pi 6 squared. So 36. So that's just 5. So 5 over pi over 36. If you calculate that out, you're going to get 0.1768. Here we're talking about radius, so that's in inches per minute, and the time is a minute. So if you pump in air 20 cubic inches per minute, the radius is going to change 0.1768 inches per minute. So that's my question. That's my answer. All right. All right, let's look at the next question. Example 4. Suppose you're standing on a pier pulling a boat towards you with a rope. So you're here, there's a pier, and then boat is on the ocean. You're pulling the rope 1 meter per second. So there's a rope right here. So I'm gonna maybe write that rope. You're pulling it towards you 1 meter per second, right? The end of the rope is 3 meters above the level that is attached to the boat. Okay. So that's 3 is here. Let me write that down. So 3 meters. So you're 3 meters above the sea level. The boat is here. The rope is connecting this way, right? How fast is the boat approaching the pier when the rope is 5 meters long? So boat is coming this way, right? And then you're pulling it here. So question is, how fast is approaching here when the rope is a certain length? So okay. So I'm going to label this as x, right? So in the beginning it probably was here, so x was like maybe 10. As you pull it, maybe x is 7, x is 6, x is 5, x is 5, 4, and so on and so forth. So question is how it's moving. So how fast is it moving this way, right? Because boat is not going up. Boat is just going forward. So that's x direction, right? So the variable is x. This distance changes, and the length of the rope is also changed. So I'm going to say this is z. You're standing on the pier, so this length is going to be always 3. So I just want to see, okay, this is Pythagorean theorem. Because you can kind of see there's like x, y, and z, look, a, b, and c squared. Like, so this is going to be Pythagorean theorem of some sort. The variable is going to be x and z. Fixed amount is 3. The height is fixed, right? So I'm going to have to recognize that. What do they want me to find? So sometimes it's kind of hard to see what are they asking. The question is, how fast is the boat approaching? So it's this directional speed, right? It's a speed, but it's this direction, not like this direction speed. So dx dt is what they're asking. The first information they give you, 1 meter per second. Your rope is decreasing by 1 meter per second, right? So that's dz dt is 1. And I'm going to say it's -1 because it's like decreasing, right? So it gets smaller, so I'm going to put -1 meter per second. And I labeled this as z. So when boat was like out here, z was big. And then now as it gets closer to the pier, now z is small here, right? So I'm going to say it's -1 meter per second. And the question is asking this. So how do they all relate? I'm using Pythagorean theorem, so x squared plus 3 squared is equal to z squared, right? Because this is my y. And basically, I can kind of do the same thing. I want dt, so I can take the derivative with respect to t. So dt x squared plus 9 is equal to z squared. So from there, I can get 2x dx dt plus 0. Again, when I take the derivative constant, you just get 0 is equal to 2z dz dt. So 2x dx dt is equal to 2z dz dt. Wow, okay. I can divide both sides by 2, so this cancels out. I'm solving for, what am I solving for? Dx dt here. So I want to solve for dx dt. So that means I'm going to divide both sides by x. So from here, I can get dx dt is z over x times dz over dt. Okay. I think we're almost ready to solve it. So what do I know? Like, let's go back, review here. There's a lot of information happening, so I want to be super careful. dz, do I know dz dt? Let me see here. dz dt is fixed, it's -1. Do I know x or z? Do I know this length or this length? I have to read it one more time. How fast is it approaching? When the rope is 5 meters long. So they're talking about when z is equal to 5. Again, depends on where the boat is. It might move at different length. So this is specifically when z is equal to 5. So there z is equal to 5. So okay. So they're saying z is equal to 5. dz is -1. How about x? They didn't say anything about this length. But I know that, so I have to do a little bit of side note. 3, 5, and x. When the height is 3, the rope is 5, how do I find x? Again, it's the Pythagorean theorem. 3 squared plus x squared is 5 squared. So 9 plus x squared is 25. X squared is equal to 16. That means x is equal to 4. Okay, so that means x is 4. So I have to kind of do extra work there. So that's 5 over 4 times -1. So -1.25 meters per second. Okay, so boat is coming towards the wall at -1.25 meters per second. That means x is getting shorter and shorter, so it's 1.25 meters per second towards here, right? So that's my final answer. I'm going to have you try example 5 yourself, and basically after that, we're done. Next question here is here. I'm not going to do all of it, but your setup is tangent theta is equal to y over x, which is basically y over 2. And then go from there, solve it, and your final answer is pi over 15 kilometers per second is your answer. This section was pretty long, and this is a lot of questions. We'll do some more practice in our meeting, okay? And we're done for this worksheet.